Okay, so for this one, we're going to be solving for x, given that the natural log of x plus 4 plus the natural log of 5 is equal to the natural log of 2x minus 7. So if you recall, the way that we've done these in class is that we need to get a certain formula that says the natural log of m is equal to the natural log of n. If that's true, then it must be true that m is equal to n as long as our domain checks out. Now this is true for any log base. Log base 2, log base 73, it doesn't matter. It's just natural log is the easiest one to write in this program. So if we can rewrite this problem as one side being natural log equal to another side being natural log, then we can set the insides of those logs equal to each other, just like we did with this m and n. And then from there, we just have to do a quick check with our table to make sure our domain is correct. So back over here, we have two natural logs being added together. Remember that whenever you have two logs being added together, we have a rule that says you can put them inside of one log with multiplication. So addition of logs of the same base is equal to multiplication inside of one of those logs. So we can change this to the natural log of 5 times the quantity of x plus 4. We're multiplying the 5 to the x plus 4 and putting it inside of one log, and that's equal to the natural log of 2x minus 7. Now that we've condensed the two logs on the left side, we now have our formula, one log equal to another of the same base, which means we can now set the insides of the logs, meaning the 5 times the quantity of x plus 4, equal to each other. So 5 times the quantity of x plus 4 equals 2x minus 7. And now this is just a simple algebra problem. We start solving for x by first distributing this 5 to give us 5x plus 20 is equal to 2x minus 7. Now we need to combine our like terms by moving the smaller x to the other side. So we're going to subtract this 2x from each side. We move the smaller one to try to avoid any negative values in front of our x's. So we subtract 2x from each side, and now we need to get the constants together on one side. So we'll subtract the 20 from each side, which gives us 3x is equal to negative 27. The 2x and the negative 2x cancel out, and then the 20 and the negative 20 also cancel out. And now to get x alone, we'll divide each side by 3 to get x equals negative 9. Now remember, for our domain, whenever we're dealing with these problems, these natural log equations or logarithmic equations in general, doesn't just have to be natural log, we have to do a check to use this formula over here. It must be true that m and n are greater than 0. That's not to say that x is greater than 0. X can be negative. It's to say that these values that we started with, the x plus 4, the 5, and the 2x minus 7, anything that was inside of the natural logs, has to be greater than 0 when we plug our x equals negative 9 into them. So this is where our table comes in. We start our table with just our x values, which in this case we only had one of them, which was negative 9. And now we need to check each of our natural logs. So we have x plus 4 for our first one. And then we had 2x minus 7 for the other one. Note that we don't have to check this one, natural log of 5, because no matter what x is, 5 will always be greater than 0. So you don't have to check the constants that are in your logs. So if we take this x is equal to negative 9 and we plug it in for our first value, x plus 4, we end up getting negative 5. And that's instantly no good. We don't even have to check the second table value because this value is less than 0. It has to be greater than 0. That's instantly a failure. So we know immediately that there is no solution. Because it fails the domain check of this formula.